Hi, good morning. Thank you for the invitation to talk to you today. What I'm going to be talking to you about is a summary of a paper that I and a bunch of colleagues of mine just finished and is now published in a journal that's called Earth's Future. The topic is about the mismatch between what we understand about climate information and what people really need in terms of climate information in order to be able to make plans. I'm thinking specifically in terms of water stakeholders here. So I'm the lead author, John Nielson-Gammon, but there's a whole bunch of other people who've been involved in this. Um, Co-authors Jay Banner, who's the head of the Coupled Natural and Human Systems Research Group at the University of Texas at Austin, who brought all of this together. A bunch of other people from UT Austin, Texas State, Texas A&M, City of Austin, etc. And this work was sponsored by the National Science Foundation and the Cynthia and George Mitchell Foundation. So the paper itself is organized around what we know about Texas climate, what we need to know about Texas climate, and what particular stakeholders desperately want to know about Texas climate. First, looking at the historical record of climate in Texas, the graph on the left shows global temperatures. The dark blue and orange colors are two estimates of global average surface temperatures. The light blue, which is somewhat smoother, is actually the average of a whole bunch of computer model simulations of global average temperature. It agrees pretty well. It seems to be running a little bit hot recently. And then the maroon colored line is basically a decadal running average of Texas temperatures. So it's smoothed by doing a decadal average, but yet it still looks very noisy because when you're talking about a small part of the globe, you've got natural variability playing a big role. Natural variability makes some places warm, some places cold, and those switch around from year to year. Smaller you are, the more likely you are to be just in a warm anomaly or a cold anomaly. But you notice since about the 1970s, which is when we actually had the coldest decade on record for Texas, temperatures have been warming faster than the long-term global average. And that's actually consistent with what climate models project. We're on land, we're going to warm up faster than the oceans are. And the warm up should be relatively uniform across the state, except for, like urban areas might heat up faster, that sort of thing. The map on the right shows indeed it is fairly uniform. Perhaps it's warmed up faster in the southern part of the state than the northern part, but really not a big difference. The rate of warming is about 0.6 of a degree Fahrenheit per decade at present. Rainfall is, of course, perhaps the biggest driver of water supply changes over time, both from year to year and over the long haul. On the left, you can see the graph of annual mean precipitation in Texas. There's a few dry years that stand out, 1917, 1956, and 2011. There's a few wet years that stand out, 1919, 1941, and 2015. In fact, if you look at the past 12 years or so, we went through a stretch of 7 years, each of which was drier than any of the following 4 years. So we had a bit of whipsaw there. It certainly looks like a lot of natural variability compared to previous decades, but you go farther back, you see the decade of the 1910s is not all that different in terms of the rapid changes in rainfall. Overall, you might be able to see a little bit of an upward trend in rainfall, and indeed the map bears that out. It's an increase of about 10% per century, which can be substantial when we're talking about water supplies. It's not uniform across the state, though. West Texas has been fairly flat, whereas it's an increase of about 10 to 20% in the eastern part of the state. Now, we tried to put this in a real long context by looking at climate model simulations that have been calibrated to long-term tree reading records that go back 1,000 years or more. And this was work that was done originally for the high plains and for the desert southwest. And we said, well, wait a minute, Texas isn't really part of either of those regions. Let's see what Texas is doing. So here's a map of West Texas. What we're looking at here is the average annual conditions for a bunch of climate models, along with an envelope of what those models are predicting in particular years. Negative numbers correspond to drier than long-term normal. Positive numbers are wetter. The red is a standard drought index, the Palmer Drought Severity Index. And that's what the tree rings were calibrated against. And they show in the model simulations, basically no long-term trend until somewhere around 1990 to 2000. And then there's a prolonged drying trend that shows no sign of letting up. Now, a lot of caveats associated with this. First off, these are model predictions, and we can only really have faith in them if they do a good job of predicting what's actually already happened. In fact, what's already happened is a 10% increase in rainfall, but you don't really see a sign of that here. Model projections say that about a 50-50 shot that rainfall will go up or go down. So that's one question mark. Another question mark is what's going to happen to global temperatures. This scenario we're looking at is a high-end scenario where basically warming is near, or greenhouse gases are near the upper end of what we might expect to have happen. So it's probably exaggerating how severe climate change might be, but it gives a good sense of the trends and lets us pick out those trends earlier on while they're happening. One other issue with the Palmer Drought Index, it's not really designed to work real well on long-term trends, especially the impact of temperature on long-term trends. So to get a separate measure of drought intensity, we also looked at the soil moisture in the top 30 centimeters of the soil and the soil moisture in the top 2 meters, and normalized it to have the same variance as the drought index. And what you can see is in West Texas, the models predict that both layers will see drying, but compared to magnitude of natural variability, the drying will be more dramatic at the 2-meter depth or the whole 2-meter layer than it will in the shallow soil. That's West Texas. East Texas is not a whole lot different, except the drying is not quite so dramatic, but still dry compared to previous conditions. Now, Ron Anderson from the Lower Colorado River Authority did an analysis of how well the springtime Palmer Drought Severity Index actually predicted inflows to the Highland Lakes, the main water supply for Central Texas. And he found there was very little correlation. So really, we're looking at a snapshot of springtime conditions here because that's what we have the long-term record of through the tree rings. And it doesn't tell the whole story even of what happened in the past. Here's another way of looking at the same information. This is the average from each of the models. And over on the right is what we call the interquartile range. So 25% of the models are wetter than this, 25% are drier than this, and the bar shows the middle half of the models. And you can see most, if not all of the models are predicting drying conditions in West Texas. In East Texas, we actually have a shot at seeing an increase of the shallow soil moisture, but deep soil moisture is projected to dry out. And what's probably happening there is we're getting more water drawn out of the deep, well, most of the root zone is, say, the 30-centimeter range, and that's not being depleted as much because of what might be happening with plants. Meanwhile, less of the water is actually making it down to deep soil layers. So that's a view of what we can say about climate change in general in Texas, or at least two of the main parameters associated with climate change in general. But if we're concerned with water supplies, we have to dig a bit deeper, no pun intended. Uh, so let's talk about why we might see these drier conditions. And in a sense, it means more droughts, but really what we're talking about is greater aridity, because drought is a temporary thing. We're talking about just sustained drier conditions. Of course, you'll have droughts on top of that, but really what we're showing is that average conditions will be drier. And decrease in precipitation would make drought worse, or increase the aridity. An increase in temperature would do that. An increase in the extremes of rainfall would increase aridity because you're going longer between wet months. And changes in the amount of plant cover. If plants become more plentiful, that would have a drying effect. On the other side of the ledger, something that would reduce drought intensity is changes in how plants are using water, because an increase of carbon dioxide concentrations means that plants are more efficient using water, and so that effect by itself would add to the water balance rather than subtracting from it, but it's outweighed by these other factors. And then depending on specifically what sort of water source you're concerned about, these last two factors could either help or hurt water supply. Changes in the intensity of individual rainfall events change the partitioning between infiltration and runoff. Changes in soil moisture change the partitioning between infiltration and runoff. So both of those can have an important effect. So for surface water supply, and in fact for any long-term conditions, we really have to start with what's going on with uncertainty. Why are we not precise about what's going to happen, and what are those factors? So we can have a sense of how much faith to place in some individual particular projection. So first off, we don't know how much carbon dioxide is going to be in the atmosphere. We don't know what steps we're going to take to mitigate climate change. We don't know exactly how strong the response to the climate system is going to be. Recent work has sort of narrowed it down to within about plus or minus 20%. So we're getting a better handle on that. We don't know what the local details will be given that the globe warms, because we're going to see changes in circulation patterns that are hard to predict. Different models come up with different solutions, as well as changes in temperature and that sort of thing. Even if we knew exactly what the future conditions were going to be locally, we then have to model it to see the effect on water supplies. And most water supply models are calibrated to historic conditions, so they may or may not be able to work properly under future conditions. And lastly, we actually care about what the supply will be, not what it might be. And so that's a combination of both climate change and natural variability, which is pretty substantial in Texas, especially for average rainfall. So there's a couple of tools that have been developed recently that can help address some of the questions of what the implications are for water supply of climate change. Like a calibrated hydrologic model for the major rivers in Texas exists now. Scientists are developing reservoir models that are aware of the hydrology inflows as well as the management regulations and procedures for determining outflows. But it's not just how much water is going into the reservoir. The demand matters to some extent. How much water people are using, that's going to change with climate change. And for that matter, a lot of the dam operations depend on allowing for the possibility of flooding. And the risk of flooding is going to change with climate change also. Here's an example of the reservoir modeling system that I talked about. This is looking at say the amount of storage compared to full conditions under a drought in the first half of the 21st century, a drought in the second half that are worst drought during those periods according to a climate model. And you can see as time goes on, the risk of drought becomes greater, and the magnitude of this difference is similar in magnitude to the effect of changes in population and how that will be influencing water demand. So the lesson here is, we worry about changes in population. We also have to worry about changes in supply driven by climate. And those all need to be taken into account if you really want to know what climate change is going to be doing or what the future looks like for water supply. That's for surface water. For groundwater, you've also got to worry about what type of aquifer you're dealing with. If it's a fast recharging aquifer, such as the Edwards aquifer, then you can have big impacts on how much water is going into it due to climate change. It's very fast responding. But if you got a slow recharge aquifer, and the example for that would be the Ogallala aquifer, then it's changes in demand that are going to determine the future state of groundwater supply. And if you're sort of in between those two extremes, you've got a combination of stuff. Demand's changing. You've also got changes in the infiltration and supply, which actually lag the climate change because it takes water a long time to percolate down and resupply the aquifers. You have to deal with changes due to past climate that haven't happened yet in terms of the health of the aquifer system. Okay, at this point, we looked at some case studies of individual water stakeholders and what they would need in terms of specific future climate information. First example, agriculture producers. They're mainly worrying about what's going to happen during the next plant or cropping cycle or the next cow-calf cycle, that sort of thing. So they care a lot about seasonal forecasts, which is not really something that someone working on climate change can really provide. They also tend to be sensitive not to so much the average conditions, but some of the extremes. Is there going to be a late frost or late freeze, for example? Are we going to have a period of sustained temperatures over 100 degrees Fahrenheit? So predictions of the chances of extreme events matter a lot, and those are usually not really readily available, either in the seasonal forecast realm or longer term. And it's hard to provide that because individual producers are vulnerable to individualized types of weather shocks. Now, they've experienced weather shocks in the past, and another bit of information to be useful is have what's happened in the past, are those indications of what's likely to happen in the future, the trend pointing in that direction, or is it just basically bad luck that there's been a severe drought recently? That sort of contextual information is often lacking. And if you are caring about longer term issues, like whether you want to shift over to a completely different type of crop, then you care about projections of crop yields under a future climate, because you want to really be able to do the cost benefit analysis of whether it's worth shifting your operation. So that's agriculture producers. Second case is large surface water suppliers, supplying water to major municipalities, for example. And most of their planning is based on providing adequate water during a repeat of the drought of record. And that's a handy benchmark because we've got records for the drought of record, so you can calibrate your models. It's going to work well. The trouble is, if drought becomes more likely in the future, then that also means that a repeat of the drought of record becomes more likely, and the occurrence of a drought worse than the drought of record becomes more likely also. So if you care about how your planning is actually reducing resilience by relying on the drought of record, you'd actually like to be able to quantify that and say, how much of a margin of safety we're losing by sticking to the historic drought of record rather than planning for something worse. Like I said, the drought of record provides a concrete target, and planning using the drought of record doesn't really play very well with all of the uncertainties that I've listed in climate model projections. How do you deal with uncertainties when you have to target a specific drought? There are ways of doing that, but they involve choices. There's no real established mechanism and certainly no established regulatory process for planning for that sort of thing. And for that matter, the regulatory models such as the WAM model are not really set up to use inputs that are being influenced by climate change. So that's another challenge that large water supplies face. At the other end of the scale spectrum, small groundwater management district needs a prediction of how much water is going to be used and how that's going to change due to climate change. And that's a challenging socioeconomic question. It's something that climate scientists can provide input information to, but the modeling of that is fairly challenging. And if you're a small district, you're dealing with a lack of technical expertise. You don't have one or two engineers on staff that can work through these sorts of numbers. So that's a challenge. And the outlooks that are received in terms of what's going to happen to the climate need to be tailored to the specific factors that are driving supply and demand for that aquifer. The last case study we looked at is regional water planning groups. There's like 16 of those in Texas, and they're dealing with complicated trade-offs among different uses of water. So one of the big challenges there is understanding the sorts of interactions that are driven by climate change. For example, you've got rising temperatures. How's that going to affect energy demand? And how is the increased energy demand going to be affecting the demand for water to provide cooling for power plants? At the same time, how is climate change going to drive a change in the mix of energy generation sources among coal and nuclear and natural gas versus wind and solar, which don't need the cooling water? You would like to have a resilient water supply to be able to deal with some of these uncertainties. So you need a tool to understand how to develop a good mix of supply choices that can be resilient to climate change. And you also have to be able to sell your plan to a very diverse group of stakeholders and public who have differing visions of what climate change means in the first place. So we looked at one example of a planning exercise that did incorporate climate change information, and that was Austin Water. They looked at a 100-year-long plan, and they took inputs of global model projections of rainfall and temperature. They were converted statistically to projections of things happening at specific gauge locations. And then those were correlated with historic stream flow using the historic data. And then the same statistical model was used to predict future stream flow given the future rainfall and temperature conditions. And those were then provided as input to the water availability model. And part of the key to the success of that was working directly with climate scientists, using the climate scientists to have them learn what were the important bits of information, what would be most valuable, and in turn helping the stakeholders and water supply folks understand what the uncertainties were and what the different ways were of dealing with them. So just to wrap up here, we posed a few potential research endeavors where we thought there were knowledge gaps that could be filled. For example, understanding how the dividing line between dry Texas in the west and wet Texas in the east has shifted over the distant past during a relatively stable climate, which is actually as warm as the present day was back 5,000–6,000 years ago. We need the tools to connect the climate model projections directly to the local stream flow and feed those into stream flow models. We need to be able to come up with some way of adjusting the drought of record to be able to maintain the same level of resilience that was codified into law and policy when we thought the climate was not changing. And we also need transparent communication between scientists and stakeholders about what we do know about climate change and what we don't know about it, so that these projections can be used with the appropriate level of skepticism. And last thing I'll mention is our paper is online, and you can Google my name, Nielson-Gammon, and the journal name, which is Earth's Future. I'm not responsible for the Earth's Future, but this is how you can access our paper. So thank you very much for your attention, and I will be happy to answer questions.